Our next presentation will be by Marvin L. Vestal of SimulTOF Systems, and he's going to speak to us this afternoon on the development of TOF-MS from intellectual curiosity to practical technique. Marvin?
Thank you. Can I ask you to do something here? Yeah, the misspelled one. Well, that's it, right there. Well, thank you very much. It's certainly a great honor to be on the program with my good friends. Those are two very hard acts to follow, but I will do my best to live up to their. And they've covered quite a lot that I don't have to do. In fact, actually, it worked out very well because the one slide of Franz's that I'm going to show, he did not show, so I get to show that one. But what I'm going to try to do is to go back kind of to the beginning of time of flight and very briefly bring up to where we are now and how we got there. And a great deal of what I'm going to talk about was driven, I think, by the invention of MALDI, because at the time of MALDI, time of flight had been around but kind of languishing and used by a few people who used it for various physical chemistry. And well, there was GCMS by time of flight by Galke with Fred McClafferty, but mostly it was kind of a curiosity that people played with, but it was not seriously used much for analytical purposes. And so MALDI really revolutionized that. Before that, TOF-SIMS by Ken Standing and other people became prominent, but it was a fairly small group of people that were involved, and it really exploded with MALDI. So I thought I would start by just kind of giving the very brief history. This is, I believe, the first paper on time of flight, and I won't read it all, but basically this was right after the Second World War, and there'd been huge advances in electronics during that time, and this gentleman recognized that this made time of flight measurements of ions practical. You notice he was talking about microsecond pulses and millisecond times, and the modern development of electronics has changed that to nanoseconds and even picoseconds and higher. He said millisecond time scale, and of course now we can go even faster than that. But I won't go into any of the detail because it's just too much. But the development of modern electronics, particularly in the last number of years, the modern digital electronics, has made an awful lot of what we do possible. And we've had nothing to do with it in terms of the development, but we've been people. We've used it as it came along to be able to do things that otherwise we wouldn't have been able to do. And so I will give you some of the results of that, but I won't tell you how to do it. But you can look. But all of that technology is now available commercially by people who do these things. The sort of brief history going back, the very first functioning instrument, I think, was this one by Cameron and Eggers. But the real milestone was Wiley and McLaren, who built this instrument, and they were the first ones that described really the theory of focusing in time of flight. And we still use today what they defined, although we keep rediscovering it periodically. But that is really the seminal paper, and the Bendix machine that was referred to earlier was built on this device. Galke used it for GC-TOF. I mentioned one of my early papers there because we did a coincidence time of flight where we detected secondary electrons and positive ions and used a modern time-to-digital converter for that, which just became available at that time. And this is the technique that Ron McFarland used in the plasma disruption work. I don't think he was aware of our work because this was a technique that came out of nuclear physics, and nuclear physicists had been using these kind of techniques before we did. That's where we got it from. And then the other really important contribution was by Marvin, which was mentioned earlier, the addition of the reflector, particularly the two-stage reflector. Single-stage reflectors had been around for a while. And then McFarland's work with plasma that Peter mentioned. And then the other, of course, we've just heard about from Karras and Hillenkamp, the MALDI, which were really big proteins fly. And that's when very many of us, I had not done any time of flight in the intervening period, but once I saw that, I said, gee, this is something that would be a lot of fun to do. So we started working on it. Raymond Kaufman was mentioned earlier, and he and Spengler were the ones that pointed out that you could get because the ions were fragmenting in flight, you could analyze these to get fragmentation, and they were doing this quite early in the MALDI period. But then the other really thing that made a huge impact was the so-called discovery of delayed extraction by Brown and Lennon, and certainly it caused a lot of us to sit up and say, wow, we knew all about that. Why didn't we do it before? I know Franz, the guy who built the pulsars that we used, had a lab next door to him at one point, I think. But he, Brian Chait, and other people, including myself, who were knowledgeable about time of flight, we said, that's so obvious, why didn't we do it? But it took these guys to sort of take a new look at it and say, you know, if you pulse the extraction, you can do some things that you can't do with continuous extraction. And so there's the QTOF and the TOF-TOF, which have come along more recently, and I'll touch a little bit on those, but I won't have time to go into detail. A lot of this stuff is now commercially available, but this was the spectrum that I saw at Bordeaux, which was, was really just, I think most of us had our jaws dropped as, I think this is the first molecular ion of this mass that was observed in the gas phase, and Franz presented this in a paper which I don't think was really advertised that that's what he was going to present, but I saw it and I thought, gee, this is pretty exciting. But I was saying, well, how could people use this? And he was using this Llama instrument, which was very expensive and was not really designed for this purpose, but it worked. And I recall, this is the only story I'm going to tell like this, but we were on the bus in Bordeaux when we went out we had this beautiful banquet in one of the caveaux, which was probably the best banquet and party that was ever held at a mass spectrometry meeting. But we were on the bus going to that, and we were sitting next to each other, and I said, well, Franz, that's really exciting stuff that you've shown, but I don't see how it's going to have any commercial aptitude. So that shows how much I know. But I changed my view very quickly because, did I? Oh, I hope I didn't skip one. Because Beavis and Chait built this simple linear instrument, which I said, wow, that's a pretty simple instrument. That's something that we might be able to do commercially. And this was the spectrum that they got with that simple linear instrument of the same compound that Franz had showed. And you can see that while it's not great, the resolution is almost the point where Klaus would say that's a real mass spectrum, and I think so too. And in fact, when Klaus saw this, he was ready to get an instrument, and he was one of the first people to buy a commercial instrument based on this design. We adopted Ron and Brian's design, and this was the first, I believe, the first commercial MALDI-TOF instrument, and Klaus Beeman was the first customer. Richard Caprioli was one of the early customers. I don't remember whether he was third or fourth, but somewhere along in there. And Randy Nelson, who's speaking later, was a recent PhD graduate, and he was our go-to guy who helped build them, install them, and work with the customers to make them work, and sometimes ran the customer samples for them because they couldn't quite manage it on their own. But so he got his start with this basic instrument and has done great stuff ever since then. I'm not going to go. I could throw up a lot of equations, and I know you'd all go to sleep. If you're interested in the theory, there's some Peter Uas and I published a paper several years ago about the theory of focusing in time of flight. I think there's 150-some equations in it. It's in, I guess, the JASMAS, I think, of about 10 years ago. And only one person that read it was Franz Hillenkamp, because he corrected our mistakes in the equations, and I think he's probably the only one who ever read through it. But basically, you can predict from the principles that Weil and McLaren stated back in 1992 how to focus in time of flight. And the thing that wasn't realized early on was that the velocity spread that you produced by MALDI was quite broad and quite high, and it was independent of the mass of the ions, at least to a very good approximation. And it was that fact that really was seminal in understanding. Well, that's why delayed extraction worked, of course, and it was the main thing that we weren't getting when we did static instruments. And even though we had the ion mirror from Donanov, it really only improved things a little bit, and all it really did was make the flight time longer without introducing any more dispersion. But the dispersion was really introduced in the ion source by this initial velocity, which was not compensated for in the static acceleration. So one of the early papers that my colleagues and I did comparing these when we first got a delayed extraction instrument working, and this was a commercial instrument that we'd had out for a while with both a linear and reflector. And I don't show the original linear spectra here because they were completely unresolved, but if you look at the middle column, the delayed linear gave higher resolution than the static reflector. And we were quite pleased with those results. And you see our reflector results were a bit better. And this bottom row is a very large instrument. This was I think the one, Ken used to call it a 14-meter instrument. It was actually 4 meters long and only had a 6-meter effective flight path. But we were very happy to get 8600 resolution out of that, and that was the best that was available at that time. And you couldn't do that without delayed extraction. And these are all the equations that you need to know if you really want to optimize a instrument. I'm not going to go through these in details, but the important thing is you have some spatial distribution of the initial position, that is the size of the crystals, for example, and you have this very important initial velocity that is really what limits the resolution. But by using the combination of delayed extraction and a two-stage mirror, you can remove the first and almost all the second order and you're only left with the third order dependence on velocity. But you have to take into account, of course, the time measurement is important as well, but there's the other factors which often depend on the details of the design, which are not taken into account. You add all these up, and they're more or less independent, so you take the sum of the squares and the square root, and you can calculate the resolving power. And we spent a lot of time figuring out how to optimize this. But one of the things that's important is still, even though you do all the focusing, the length of the drift space does have an effect, and this DE term is the length of the flight path. So the longer the flight path, everything else being equal, you'll do better. And we've calculated the ideal conditions for different sizes, and the 3.2 meter is kind of the typical size of a laboratory instrument. Many of these are now available commercially from a number of vendors, and this model predicts that we ought to be able to get resolving power of about 60,000, but I think about the best that's been observed for this is somewhere close to 30,000, and it's true of the other sizes as well. We predicted that if we built one 70 meters long, which has been divided by 10 there, but we could get 1 million resolution with a 70 meter. And at one point we considered building it, but then we decided it probably wasn't that practical. But we did build a 14 meter instrument, which predicted a resolving power of a little over 200,000. And again, we got within about a factor of 2 of what we predicted. But one of the driving forces is, with a single reflector, it doesn't much matter how long you make it. You've got an ion source and a mirror and a detector, and it doesn't cost much to make it longer, except if you got the space. And so this is a typical spectrum from a modern 3.2 meter instrument showing 20 to 30,000 resolution over the peptide range, and fairly broad high resolution. And I say you can buy this from a number of vendors now, something of this sort, and it is now routinely, and the sensitivities are quite good, and so for high resolution and reasonably high mass accuracy. But this is our large machine that we built. This is a 14 meter effective flight, and of course it's 6 meters high, and our ceilings weren't that high, so we put the mirror on the second floor and the ion source on the first floor. And this is located in what was my office cubicle, so I guess I was there saying, what happened to my office? But I think this instrument, I believe, holds the present record for resolution in MALDI. And typically for this, I've picked a very the sort of result we get all the time, except this is probably the best we ever saw. So take that with some salt. But you see, this was a triptych digest of BSA, and the resolving powers are up to just around 100,000 or a little bit less. And if we looked at low mass, where we had really tweaked it carefully, we got up to, I guess, 140,000 or so on some low mass ions. That instrument is still functional, but we've kind of moved away from using it very much. And the mass accuracy, it turns out, does not depend too much on the resolution and the length, as long as you don't have things that are not resolved. And we've produced this sort of an effect several times. If it does depend a little bit on sample prep, but you can typically get RMS errors of on the order of 1 ppm to 2 ppm with a few outliers. So 1 to 5 ppm with a good reflector is now quite routine over a broad mass range. You do have to do some automatic internal calibration where you have at least one reference peak to correct for small changes in position of the sample, et cetera. But this also is pretty much available commercially from existing instruments. This is quite an interesting instrument that recently was done by JOL, and this is based on a design from Matsuda and Matsuda, which goes back many years. They developed this in Osaka, and JOL has made a commercial instrument. Now, this is actually a 17-meter effective flight path, and the ions go around this spiraltron and then are detected at the end. And they also have an MS version of this as well. And say this is a slightly bit longer than our 14-meter and gives very comparable results. This is some results from their measurements. I guess you can't really see the resolution there, but it's on the order of 60 to 80,000, and I think this is their plot of resolving power versus mass, and with different delay times. So if you make the delay time longer, you focus at slightly higher mass, so the one that is the triangles there is the longer delay time, and that goes up to about 80,000 resolution at mass 2500. So they can resolve the isotopes quite well and with good accuracy. So the status of high resolution MALDI now is, as I say, it's quite common and commercially available. The resolving power of 20,000 or more is available. You can go up to 100,000, but I'm not sure it's actually practical, although perhaps it is. Perhaps with a JO instrument you might say. But there is a problem with, as you make the flight distance longer, you tend to be trading sensitivity for resolution because these ions are mostly metastable, and a lot of them don't survive that long, so you lose a lot of ions along the way, and so there's always that trade-off. Now, perhaps a different matrix and so forth may help, but that is one of the limitations. And it really comes down to that generally the sensitivity is limited by the chemical noise, so you can get down to the sub-femtomole level fairly easily, and whether you get below that or not depends a lot on the matrix preparation. But resolution, of course, helps you because the chemical noise usually has a different mass defect, so you may be able to pick them out of the range. And so often one can get down to the 1 attomole sort of level, and this is 1 attomole per microliter put on a plate. You're not necessarily looking at the whole attomole, but that's all you put on the plate. If you look at the whole sample, you can do somewhat better, except that chemical noise doesn't get any better as you take more spectra. So when you go to the linear analyzers, size matters really more because the velocity terms are not the limiting things in general, except at low mass, and so the longer you make it, the better everything works. And this is a calculation of resolving power with different, the number on the top there is the mass focus. This is the time delay is set to focus optimally at mass 3 kilodaltons to 60 kilodaltons. And in the low mass region, you can get peptide isotopic resolution, but at the higher masses, you don't get high enough resolution to resolve the isotopes, so you see a peak that's the width of the isotope cluster, and typically on the order of 500 to 1,000 is the routine resolving power you see in linear instruments. This is an example of about the optimum we've seen on a linear instrument with peptides, and where we're getting up to about 8,000 in the middle. And it's further mass dependence because the first order velocity focusing only is mass dependent. And you can see we're going from 5,000 or so to 8,000 over this mass range. And if you go outside this, the resolving power continues to fall off. But this is higher resolving power than we were getting with our really huge reflector instrument in the early days. Of course, we didn't know how to build the reflector very well in those days, so we have improved that, and a lot of other people have as well. One thing I wanted to mention is this detector, which I think I see Bruce back there in the audience. This comes from Photonis, which is a hybrid detector, which we found very useful, particularly for linear. And the original idea we had with this is that, the folklore is you can't detect these high mass ions because they're going too slow and they don't knock off any secondary electrons. And so this detector, in principle, we can post-accelerate the ions up to an additional 30 kilovolts. So we can start off at 30 kilovolts, accept them up to 60 kilovolts, and then have the electrons hit a scintillator, and then the scintillator couples to the phototube back down at ground. But we found that we didn't really need to do the post-acceleration, that 20 kilovolts was enough, and we got plenty of electrons, and we could detect things. It was shown here. And this uses a fairly fast scintillator, so the peak width, full width at half maximum, is on the order of 1 to 1.5 nanoseconds. And we're using this routinely now in the linear instruments, and it works very well. This is an example of BSA, which is everybody's favorite. And you can see that we're seeing up to the trimer at 190,000, and I don't have spectra, but we've looked at IgGs and even IgMs. And as far as I know, you can detect any ion that you can make, provided you can make it fly down the tube. There are some more exotic detectors that have been proposed, but and of course, using secondary ions instead of secondary electrons does gain you some sensitivity, but it costs you some resolution. So, but some of the other detectors, like superconducting detectors and so forth, which are quite interesting, but I think and nobody's ever shown a very practical version, and I think they're totally unnecessary because you can detect the ions. Despite what we were told 30 or 40 years ago, that these ions wouldn't produce any secondary electrons, they in fact do produce secondary electrons. The sensitivity is not 100%, but it isn't for anything else either. So what we've been looking at recently is quantitation by MALDI in the linear system, and this is a series of spectra on saliva, which we've picked as a biological sample, which we, in a place where we don't have a lot of biological samples, it's easier to get people to spit it in a tube than it is to take their blood. So we've been looking at saliva. And this is 6 spots across the plate where it's the same sample, but we're just looking to see, and this is not processed, this is sort of the raw data, but we've acquired 10,000 or so shots, if you can read the fine print there on each one. And these are 6 superimposed, and so you can see that, well, there is a little difference, particularly in the lower peaks. The spectra are really quite reproducible. Now, this kind of flies in the face of some of the conventional wisdom, because the conventional wisdom that many people have heard and many people here may even believe, I don't know, is that MALDI is not quantitative. That it's okay, you get useful results, but for quantitation it's just not useful and you shouldn't even think about using it. Well, in one sense that's true, because the way we used to do MALDI with nitrogen lasers or other lasers that operated at very low rates, and where you only took a fairly small number of shots in what I call the hunt and peck method, where you looked at a sample and found a sweet spot and took a spectrum, and then you moved to another spot and you got a different spectrum. This is 4 different spectra of 50 shots each on one sample spot, but moving to different places on the sample. And you can see the intensity varies actually by about a factor of 20. And this at 10 hertz, it would take 20 seconds to produce this, and this is about as long as people would do it. But you can see that, if you look at this, you say, well, gee, this is not quantitative. And in fact, in many samples, you would see different spectra from different spots, so that's even more complicated. So this is where this conclusion comes from, and it's perfectly valid if you do it that way. But what we've been trying to do is to correct that. So this is we've now done some processing. We average over the spot, process the data a bit to do some normalization, and this is 4 different sample spots superimposed, and one of those is the same sample spot that was used in the previous slide. And if you look very carefully at the blow up there, you can see there's a very small difference that you can just detect in that, but essentially these are 4 exactly reproducible spectra from 4 different sample spots. So in linear MALDI, we can say that the resolving power is mass dependent. You can get up to 5,000 to 8,000 over a limited range at low mass, but at higher masses you're limited to 500 to 1,000. And each spot, you can take up to 200,000 shots off of a spot before you exhaust it. So, and you usually don't do that much because you get tired of looking at it before then. But if you're really trying to get the most information out of the sample and use the sample, then you will do more. The mass error is typically less than about 30 ppm, and provided you do some single peak automatic calibration. And that one that I showed earlier, I forgot to mention it. In some cases, you can see up to a dynamic range of up to 100,000 between the largest peak and the smallest peak that you can detect. And my contention is that the combination of the high laser rate and data processing does in fact make MALDI quantitative, and I think quite competitive with other techniques for quantitation. I'll just briefly touch on TOF-TOF. Spengler and Kaufman pointed out many years ago about the fragmentation in MALDI, and they used programming the mirror to focus different sections. And about, I don't know, what is it, 2001, I guess, but about 12 or 14 years ago, we built a TOF-TOF, not of this design. This is a more recent one where we used two reflectors. A first reflector is focused where it says the first focus there, and then that's where we select the ions. Then we do some additional acceleration, fragmentation, and then analyze the fragment ions in a second reflector. And this works quite well in one sense, that as we get quite good precursor selection, the upper one is the full spectrum with no selection, and you blow up of the one of the peptides. And one of the things we can do with this is multiplex selection, because we can pulse the selector multiple times for each laser shot. So we can select up to 10 different peaks and look at the fragmentation of all 10. Now, of course, these fragment spectra overlap, and it's a little bit of a challenge to deconvolute them. But for some MRM applications, it actually works pretty well, and you get much better utilization of the sample, because unlike the other MALDI stuff that I've talked about, where you are looking at all of the spectra all the time, once you do MS-MS, you're picking only one ion, for example, out of the spectrum and throwing the rest of them away. So you're not using the sample as efficiently. But by multiplexing, you can make this more efficient. But there is always a downside to something of high resolution, as you often pay the price in sensitivity. This is just comparing the spectra between selecting one peak and selecting the isotope envelope. And in fact, I should have blown this up, but the only difference is you don't have quite as many ions in the second one because you're throwing the higher isotopes away. But the real problem is this is just to show that you can get actually very useful fragmentation out of this. And I think Franz mentioned earlier the high energy fragments giving I guess it was Peter actually that mentioned the D, V, and W ions. And in this case, you do have some D ions, which you only see if you have collision-induced dissociation, and that D5 ion tells you that it's an isoleucine and not a leucine there in the middle, if you care about that. There's some other D ions in here as well. But the spectra are quite the same as you get from other fragmentation techniques, whether electrospray or whatever, except we're nearly always starting with singly charged ions. But this is the problem, which is still to some extent unresolved. With the dual mirror TOF-TOF, and I think also with the JUL high resolution front stages, you throw a lot of ions away in the process of getting them to the selector. So we got a perfectly good spectrum, but we took 529,000 laser shots to get it. We didn't have to take quite that many, but that's what this particular one was. And with the linear first stage and reflector, we get essentially the same spectrum with 1,000 laser shots and at least 200 times the sensitivity. And this is what we've observed fairly routinely with this. So we still would like to have both high resolution precursor selection and high sensitivity fragment, but so far we don't have that. So the status of TOF-TOF is summarized here. There is a trade-off between high resolution precursor selection and high sensitivity for fragments. The 5 kilohertz laser, which we're using routinely now, anywhere from 1 kilohertz to 5 kilohertz, makes a lot of this stuff practical because you can use the sample more efficiently because the old MALDIs, you leave most of the sample on the surface. You have to put it on there to make it work, but you leave most of it behind. With a high rep-late laser, if you need to, and in some cases in LCMS, you do. You can use 200,000 shots or even more and get all of the sample into ionization in the gas phase. I guess I didn't show it, but we've generated some data where we get up to 10% efficiency in terms of the ion production and transmission for peptides, at least, in a well-designed MALDI instrument. So the efficiency is quite good, but of course you have these limitations. The multiplexing helps, but it really is only practical for MRM where you're looking for particular fragments and you can arrange it so you don't have things that you have to deconvolute. We've looked at trying to deconvolute the multiplex spectrum, but it gets to be, so far I would say it's not a solved problem. And we get, of course, both low energy fragmentation, what used to be called PSD, which generally are more useful from a structural point of view, but you also get the high energy ones which give you additional information, in particular the ammonium ions as well as the side chain fragments. And I have to say that the present status is there are a number of commercial instruments out there, they work, people are using them, but it's not as widely accepted relative to electrospray with traps as some of the other MALDI techniques are. And that's partly because electrospray with various traps works extremely well, and people tend to use whatever they have that works well. But TOF does have a role to play, I believe, but it's not as prominent as it might be. Actually, I think I picked up, I had one more slide that I guess I left off of this. I didn't get that one copied, but my other slide listed a series of applications of MALDI which are either being done or that people have talked about doing. And I will end there and leave that for Richard and Randy to tell you about what all this is really good for. So thank you very much.
We have time for some questions.
So 529,000 laser shots must be some kind of a record, Marvin.
Oh, no, we've done a lot more than that.
I'm waiting until the next talk when I hear about 1 million laser shots.
Well, we could do that. Now, not necessarily on one. It depends on the size of the sample spot, but you can do that if you want to. And of course, at 5 kilohertz, it doesn't take so awfully long to do that. And if you're doing, we wouldn't usually do that for one peptide, but we often take 20 MS spectra off a single spot, and there we may do 200,000 or 300,000 shots total to get good.
For quantitation, seems to me that the biggest help is to think about what we do for quantitation in an LC mass spec or a GC mass spec. Use internal standards. So any thoughts about the use of internal standards?
Well, absolutely. I mean, that's what Randy's been doing for years, and he'll, I'm sure, talk about that. Yeah, if you want to do good quantity. But first of all, you have to have a reproducible spectrum, and that's what I was trying to show here. Actually, I had a few more slides that show the difference between the way it was and the way it is now in terms of, if you look at one of these spots and you look at the individual shots, it looks like grass, but if you pick out a few of those, you say, well, this is not reproducible. But if you integrate over all of them, it's damned reproducible. And that's the point. So what we've been able to show recently is that the spectra, everything done reasonably, are quite reproducible. That is the same sample in different spots. Now, there is a sample prep issue and so forth. They're not, but if you take the same sample, spot it multiple times, you can get exactly the same, exactly as close as anything is exact, the same spectrum on all of those spots. Now, if you look at, and I'm going to talk about this tomorrow at a different meeting, if you look at different people's saliva, you see a lot of the spectra are exactly, a lot of the peaks are exactly the same, but there are also some peaks that are different. And that's where it comes in, of course, is that that's what you want to see is how am I different from you or how am I different from where I was? And that's where a lot of the quantitation is being done. But if you really want precise quantitation, as in any mass spectrum technique, you need a standard of some kind, whether it's something already in the sample or something you add to the sample. We as good analytical chemists know that. Not all mass spectroscopists who work in biology know that, I'm afraid. Well, the high laser rate just allows you to get better statistics in a finite time. So you use more of the sample, and if you use more of the sample, you get more quantitative results because we sum all of those so the variation across the surface goes away because you're averaging that out.
So I heard that detection TOF instruments can be a limitation also
The detection?
Yeah, the detection itself.
Well, it can be, but that's why I mentioned this detector, because it doesn't saturate readily at all. So, if you, one of the problems has been if you have a lot of low mass ions, you may not see the high mass ions because the detector doesn't respond. That's true with the dual channel plates in some cases, but that's more often with the ionization mechanism, because when you have a very complex mixture, some things fly better than others, and usually the lower mass things fly better than the higher mass things. So, if you look at an unseparated sample of serum, which we've done, we see the HSA and some of the other high mass proteins, but they're relatively weak because the lower mass things eat up all the matrix, and those don't fly as well. If you dilute the sample, those come up relative to the things, and you get something closer to the actual amount. But it's not so much a detector, but there are ionization effects, and you have to figure out what's important. But when you look at these very complex mixtures like serum or saliva or anything else, there's thousands of proteins in that mixture. You don't see all of them, but you do see several hundred very easily.
Thank you again, Marvin.
You're
And,
welcome.
we'll reconvene at 3:35 promptly.